right, so please take a seat so we can start today's class. So welcome to today's class in Mathematics 1. As you know, we won't cover any new topics this week, so here's the plan for this week. Today, I was planning to talk about exercise homework 8.2, as some of you have asked for that. So this is this question here about the orthogonal projection. And I'll also talk some more about least squares and the orthogonal projection method involved with that. Plus, we'll have one more example of the least squares method for you to try. Then, as you know, there has been a quiz that many of you have taken already. Thank you for doing that. Few comments about the quiz before we start with that. First, you will have noticed that there are some problems in the quiz that had randomized numbers in them. Of course, that makes it very hard to control the numbers that will be in the outcome or in the intermediate steps. And that means in some of the examples, quite a few of the examples actually, the numbers became, let's say, not very nice to do computations with. Of course, that would not happen in the exam, right? In the exam, I will make sure that all the numbers are nice if you do it correctly. In the quiz, for its randomization reasons, that was unavoidable. So if you had to resort to using a pocket calculator, that's totally fine. Also, you have already asked to see some of the quiz problems, and we will discuss some of the quiz problems. I'll start with quiz question 14. That was a question about matrix representation, hopefully today. And I've also selected some questions from the tweetback that I've collected that I'd like to answer today. On Tuesday, we'll go on to cover more of those quiz questions and also some exam problems that I've selected. So from former exams, not from this year's exam, of course. And on Thursday, we'll go on with that. I'll cover more tweetback questions, hopefully cover all the remaining questions. And then we can either talk about more quiz questions if there is a need for that, or we can talk about some other exam problems and see how you would do there. Two more organizational remarks. Tomorrow, unfortunately, I can't do the lecture myself due to private reasons. Instead, Alicia will cover for me. For technical reasons, we will not be able to provide a live stream for tomorrow, just because she can't set up the equipment with her own notebook, and I can't leave her my notebook. So there will be no live stream tomorrow. Of course, the notes will be on Moodle afterwards, maybe with a slight delay. But we will put the notes on Moodle afterwards, so you can take a look at that. On Thursday, I'll do the lecture myself again, and hopefully there will be a live stream then. And the second part, I'd also like to mention that the evaluation is currently still online, so you should all have received a link and a code. And I'd like to encourage you to take part in this evaluation, because it will give very valuable feedback from me and hopefully also for you. If there's some reason to change things, let me know. Especially, please do use the comments, the text fields, to put in suggestions or criticism. Mention anything you don't like. Feel free to make suggestions on how to improve this course and what I could do to make this experience better for you. We'll also take a look at the evaluation results, hopefully sometime before Christmas, once the evaluation has ended and once I have the results. Last day to do this is this Thursday, so the evaluation will be open until Thursday at midnight. And once again, this Thursday, we will have a regular exercise class, and the exercises this Thursday will be on sheet 8, and of course on all other questions you might have. Okay. So that's about organizational stuff. Hope I didn't forget anything. So let's jump right into homework problems. H82. So in HA2, we had 2 points and a line, PQ the points and G the line. And your task was to determine the length of the orthogonal projection of a line segment onto that line. So it's all in R2, so it's easy to make a nice sketch. That's what I tried here. So here's the points P and Q. This here is the line segment that we want to project. And here is the line G. And geometrically, what the projection does is basically it finds those points P prime and Q prime here, right? That connect to G with the perpendicular line. So this is perpendicular on G. And then this here, the green thing, this is the projected line segment. And we want the length of that. And basically, I could think of 2 ways to approach this. First one, you could just compute the projection of those 2 points onto the line, get P prime and Q prime. And then, of course, you also have the line segment, and you can compute the length of that. That's probably the most straightforward way. Another possibility here, you could also not project those points, but instead kind of translate that line segment to the origin. So you get the vector corresponding to that line segment here, and then you can project that. So basically all you need to do is project this point here, and you get the projected vector here. It's not quite the same thing. Yeah, as you can see here, that line segment is translated a little compared to this one, but of course the length of those 2 is the same. And as the question only asks for the length, both approaches will work fine. All right? So that's the idea. And maybe let's go over how to compute that quickly. I'd say maybe we take this approach here, simply because it's more work and more complicated. And basically this is just a little part of it. So you should see all the same techniques in both proofs. All right, so what we do is we want to project 2 points, P and Q, onto that line. And to do a projection, one method that we can use is we find an orthonormal basis of that space that we want to project onto. And then we just project onto all the basis vectors and add the result. In this case, the line is only 1-dimensional, so the basis just has 1 vector in it. That should be simple enough. Right, so first is find an O and B for G. G is a vector space, so it has a basis, and then it also has an orthonormal basis. Here, G is the span of the direction 1, 1. And to find an orthonormal base just means, well, we have to normalize that vector, right? So we normalize that to get G equals the span of, well, the norm of that is square root of 2. So this is an O and B. All right. And now we can compute the projections. So let's project P to get P prime. The point P is given by, let's see, 3 minus 2. So technically what we're doing here is we take, let's see another color here, we take this vector here, this yellow vector, and we're projecting that, right? So the result of the projection will then be this vector. I hope you can see that. Okay, so what we want to do here is we want to compute this P prime, and we get that by computing the scalar product between P and our ONB of G, or one of those vectors. And then this is the length of the projection, and of course the corresponding vector is just that ONB vector. Right, so that will be the projection. And as usual, we take out those two factors, we combine them into 1/2. And then we have 3 minus 2 and 1, 1 times 1, 1. Right, so what we get here is, let's see, 1/2 times, that's 3 minus 2, that is 1, times 1, 1. So that's just 1/2, 1/2, right? And if you look closely enough at that, that could be approximately right. The drawing's a little small to actually see that. Okay, so that is P prime. And then we can do the same thing for Q. So next is project Q onto Q prime. Q is, let's see, 6 minus 3. So Q prime is the scalar product of Q and that ONB vector times the ONB vector. And again, I take out those factors, 1 over square root of 2. I get 1 over 2 here, times Q is 6 minus 3. And we have the vector 1, 1 in here and 1, 1 out there. And so what we get is 6 minus 3 is 3, so that's 3 over 2 times 1, 1. And once again, what we are computing here technically is the projection of this vector here onto the line, so we get this red vector here. Right, that's Q prime. And then, of course, we can just compute the length of the resulting line segment by saying we want the norm of Q prime minus P prime. And that norm is, well, that's 3 over 2 times 1, 1 minus 1 over 2 times 1, 1. Remember, P prime was 1 over 2 times 1, 1. So we get 1, 1, and the length of that is square root of 2. Okay, and of course, if you use that other method, you will get the same result. Only difference is you only have to do one projection, but you have to compute the translation beforehand. Not complicated. Questions? Yeah. So the question is, if you don't have just one vector in that span, so if it was not a line, for example, but instead a plane in R3 or something like that, what do you do then? And the answer is very much the same thing. You would first find an orthonormal basis for that vector space. And of course, that would now not just contain one vector, but 2 or 3 or more, right? Still find an orthonormal basis, you know how to do that. And then in your projections here, you would compute the projection of the point onto each of those OMB vectors and add them up. Yeah, very similar to what you do in Gram-Schmidt actually. That is actually what happens in Gram-Schmidt. Yeah? You do a projection to a subspace. You just add all those up and then you have the projection to the subspace. And that's it. So same method, just gets longer. Any other questions about this? Yes. Exactly. You can do that. You can first compute the vector PQ. That's what I was trying to explain here. So if you compute the vector PQ first, basically that's this vector here, right? Vector always starts at the origin. And then you do the projection, you get this line here, different line segment, but the length is the same. So if I'm only asking for the length, that's totally fine. If I'm asking for the actual line segment, of course, that would not be the right answer. Any more questions about A2? Yes. Why do we have to normalize the span first? So basically what we want is, let me explain it differently. So this projection method via the scalar product, right? What I said is geometrically the scalar product is the length of a projection onto a space. Strictly speaking, that's only true if we have an OMB for that space, or a normalized basis at least for that space. Because otherwise, of course, the length of those basis vectors would also influence the length of the projection. Right? If I wouldn't normalize, the result would be different, because you would have that additional factor in the basis vector that I normalized out. So you get a longer result than is actually correct. Yeah, and that's why I normalize. Any more questions about this? Good, so I hope that clarifies your confusion with A2. Then maybe let's take a look. Oops, sorry. Yeah, actually we can do that. Well, I did want to switch here. Let's talk about orthogonal projection, another method for doing that we've used with the least squares method. And of course, in that least squares method, you could also do the formula that we've just discussed. Usually it's easier to use the one that we've been talking about now. So in that special case, you'll usually use that formula. Otherwise, you'll usually work with the scalar products, like we just did. Let me first explain where this comes from. So this is an excerpt from the lecture videos, basically. In this specific case, you remember the setup for least squares method was we have a system of linear equations like ax equals b. And it turns out this is infeasible. So we want to get something like an approximate solution. And more precisely, what we want is we want to change the right-hand side to some b hat, such that the system becomes feasible, and such that the error that we make is as small as possible. Right? So basically, this norm that will be minimized. Just move that out of the way here. That's the idea of this least squares method. And let me see, I do somewhere. I'll get back to that later on. Just a small look ahead. What that basically does is, let's say you have a couple of measurements. So those orange points here, those are measurements, right? And you suspect there is a relation between those two data points. And in this case, we suspect there is a linear, affine linear relation, right? So those can be described in the form function of x equals some alpha times x plus some beta, with yet unknown parameters, alpha and beta. So if the measurements were exact, the points should all be on a line like this. The measurements are not exact, and that's why they're not on the line, but just close to the line. And of course, that means if we just naively substitute those measurements into that formula, and then try to solve the resulting equation system, we get infeasibilities. If we're using more than 2 points, of course, right? You know, in this case, 3 points, so that system will be infeasible. There's no line that contains all 3 points. So what we do is, we want to find a line that is as close to those points as possible, meaning the errors that we make. So these red bars here, those are the errors that this line has compared to the measurements. The sum of all these errors needs to be minimized. And more precisely, the sum of the squares of those errors will be minimized. And that is exactly what the least squares method does. So it gives you a new system of equations or a set of parameters, of estimations for your parameters, such that the result that you get, the function that you fit it to your parameters, is as close as possible with respect to this least squares error measure. Right? And technically what happens here is we project B onto the column space of this matrix A. So this B hat is the projection of B onto the column space of A. And of course, if something is in the column space of A, that means it is a linear combination of the columns. So there is an X such that this equals B hat. Right? Remember that is basically, this expression basically means we compute a linear combination of the columns of A. So that's why we want this projection. Okay, so how can we obtain that? Of course, we can use the formula that we've just seen. In this case, we can make our lives a little easier by using a different approach. And that is the following. So assume you have a vector V. You want to project that on some space U, like this one. And you want to have this projection, and you want the orthogonal part. So you want to decompose V into some vector U that is in that orange space and some vector U ortho that is orthogonal to that orange space, whatever the dimension is. And let's say we have the matrix A that describes our space U. So U is the column space of A, meaning the span of the columns of A, right? So here we have the vectors U1 to UK. Those are the columns of that matrix A. Now what we need to find then is we need to find some vector in the column space and some vector orthogonal to that column space, such that V is their sum, and such that U, this first part, is a linear combination of the columns of A, right? Meaning it's in the column space. So we need to find coefficients such that U can be written in this way, or in other words, U is A times X. And X are the coefficients we're looking for. And also, we want this remaining part here to be orthogonal to U. So we want that decomposition of V, and we want this U ortho part here to be orthogonal to all columns in A. So this relation has to hold for all columns of A. Right? And we can express this in this way here. We can simply write this is A transposed times U ortho. Remember, those are the columns of A, so those are the rows of A transposed. And if you do matrix multiplication, you always multiply a row of the left and the column of the right matrix, right? So here we multiply all the rows by this vector, and that means we're taking the scalar products. Each row of the result will be a scalar product of one column of A, or one row of A transposed, with this U ortho. And the condition is all of these need to be 0. Okay, so in short, we can just solve this one here for U ortho, like this. U ortho is then V minus AX. And this is just the second condition, A transposed U ortho equals the all zeros vector. And now we take this and substitute it in here. And what we get is this here. Oops. This here. Or if we multiply that out and reformulate just a little, we get A transposed AX equals A transposed V. We know A, we know A transposed, we know V, so this is just a linear equation that we can solve for X. And once we know X, we can easily compute U, just AX, and U ortho. So that's what we are going to do. We're going to solve A transpose AX equals A transpose V. And then we say, well, U is just AX, and U ortho is V minus AX. Right? So in our specific case, remember we wanted to compute the corresponding B hat. The B hat that we're looking for would then be this AX. Okay? So this is where this different formula for doing projections comes from. You can also use that, and usually you'll use that if the space that you're interested in is given as the column space of a matrix, and you want to project onto that. The upside of that is you don't have to compute an O and B beforehand. Yeah, no need to do that. It's all automatically in that formula. So in this specific setting, this is probably the easier approach. So let's take a look at a little example. Let me just explain the setup briefly. So we've already seen that graph here. Again, here's a couple of measurements, and we want to find, we suspect there is a law that basically governs those measurements, and we suspect there is a relation between X and Y value that looks like this. It's linear plus some translation, right? We don't know the parameters alpha and beta, and we'd like to determine those alpha and beta such that this error that we make here and here is as small as possible. So we're using least squares error measurements. In other words, we want to minimize this here, right? And the task is to compute the right values for alpha and beta. Now, how would you go about that? Again, here's the table of measurements. Let me maybe show you the first step, and then let's see if you can get the rest done alone. So again, what we want is this relation f of x equals alpha x plus beta. We want to determine the right parameters for that. If we just put in those values that we have here, so we know that f of x1 must then be alpha x1 plus beta, and f of x1 is y1, right? That's given. So here's x1, here's y1. And if you put in those values, what we get is alpha times minus 2, that's x1, plus beta equals 5, that's y1. And of course, we can do the same thing for the other values. So if I put in x2, I want y2. x2 is 1, so we get alpha times 1 plus beta equals 3. And then we get f of x3 equals alpha x3 plus beta equals y3. So x3 is 2, that means 2, x3 is 2, that means 2 alpha plus beta equals, and y3 is minus 2, so that equals minus 2. Right, so we have these three equations, and if you do the computations, you'll see the system is infeasible. So the system that we have here in matrix vector form looks like that. Let's see. We want a matrix. We want to multiply that by alpha beta, and then the right-hand side, that's the y's. The right-hand side is then 5, 3, minus 2. Right, that is those y values here. And for the coefficient matrix, we need to use those values. So what we get here is minus 2 and 1 beta, 1 alpha and 1 beta, and 2 alpha and 1 beta. Right, so this here is our matrix A. This is our vector B. And that here is the X, the unknown that we're looking for, in this case alpha beta. And again, I said this is infeasible. So the task is find the least squares approximation for that. Preferably using the method we have just discussed. Okay, so let's see if we can solve that from this point on. Again, here's the data if you need that anymore. I'll give you a few minutes to think about it, do the computations, and then we'll see whether you get the right results. And maybe let me also mention the right results don't look very nice. It's hard to have nice numbers in problems like that. And for those who are already done, there is a quiz on Tweetback where you can check your results. Okay, quick announcement. I just found out that apparently there's a typo in my solutions. So forget about the quiz values. Just go on. We find the right result later. Just a quick show of hands. Who is done already? Who would like some more time? So let's give it a few more minutes then. So maybe one more minute and then we'll take a look at the solution. All right, so let's see if we can find a solution together. Before we start, quick show of hands. Who thinks they have a correct solution? Wonderful. Good, so remember, what we have to do is basically we have to solve the system A transpose AX equals A transpose B. Right, so first thing we need to do is, of course, compute the coefficient matrix and compute the right-hand side of this. Okay, so let's start with A transpose A. Here's the matrix A again. A transpose is then simply minus 2, 1, 2 in the first row and 1, 1, 1 in the second row. I'll just copy A here. The result will be a 2 by 2 matrix. So let's see, what I get is if I multiply this row with this column, I'll get 4 plus 1 is 5 plus 4 is 9. Then for the second row and the first column, I get minus 2 plus 1 is minus 1 plus 2 is plus 1. For the first row, second column here, I get minus 2 plus 1 plus 2, that's again plus 1. And finally, second row, second column, that's 1 plus 1 plus 1, that's 3. Quick sanity check. If you do this, the resulting matrix should always be symmetric, because A transposed A is symmetric necessarily, right? If you transpose that, by the rules of transposition, you get A transposed times A transposed transposed. So that's again ATA. Right? So that means this here is always symmetric. If yours is not symmetric, you've already messed up. Don't continue. So next we need A transpose B. You can just copy A transposed. And B is that vector here. So 5, 3, minus 2. And that is, let's see, that is minus 10 plus 3, that's minus 7, minus 4 is minus 11, is that right? You'll stop me whenever I make a mistake, hopefully. And then we have 5 plus 3 is 8, minus 2, that should be 6. All right? Good, so now we have our equation system. So we solve A transpose AX equals A transpose B, simply through Gaussian elimination. A transpose A, 9, 1, 1, 3. And the right-hand side is minus 11 and 6. And I'll first swap those two rows here because I'd rather work with the 1 as a pivot element. So we get that here. And then I subtract 9 times the first row from the second. And that gives me, let's see, that is a 0 here. 9 times 3 is 27. 1 minus 27 is minus 26. And 9 times 6 is 54. So I have minus 11 minus 54. That is minus 65. Is that right? Good. Should bring a pocket calculator for those lessons. And if I'm not completely mistaken, both of these can be divided by 13. So let's do that first. 1, 3, 6. And actually minus 13 would be even better. So that's a plus 2. And 65 is 5 times 13. So we have a plus 5. All right, that looks much nicer. Okay, now we can solve. Our second column corresponds to the beta variable, so we have 2 beta equals 5, or beta equals 5 over 2. And then we get alpha plus 3 beta equals 6, or alpha equals 6 minus 3 beta. And that is, let's see, 6 is 12 over 2. And we have beta is 5 over 2, that's 15 over 2, right? That means we get minus 3 over 2. Okay. You still agree with me? Good. So that's our parameters. Alpha is minus 3 over 2. Beta is 5 over 2. And we don't even need the b hat, right? Because all that was asked for is those two parameters, and that means that's our solution. And maybe let's have a quick look at the sketch to verify those could be approximately correct. Yeah, it doesn't look that bad. So I mean, that of course is just a quick guess by looking at the points. But usually you are able to take a quick guess at how that line would approximately look like by just looking at the points. And I can verify that your parameters don't seem too far off. And in this case, where we do have a negative slope, minus 3 over 2, that could be about right. And the beta is about 5 over 2, so that should be somewhere here. That also looks about right. Okay, so that is the line that you will get from this least squares computation. Any questions about that? Otherwise, next point on my list is a couple of your questions that I'd like to answer very briefly. And then we'll take a look at least one of the quiz questions, and we'll go on with more quiz questions tomorrow. And that should also answer one of the questions that have been asked. Okay, first question that I took from the tweetback. If a vector is two-dimensional, sorry, if a vector space is two-dimensional, and the dimension of the image is 2, and I'm guessing the image of some f, right? In the exam, are we allowed to argue that because of the rank nullity theorem, the dimension of the kernel must be 0, and therefore the kernel is 0? So setup is, we have some f, two-dimensional vector space to, I don't know, whatever the codomain here is. This is two-dimensional. And we know the image of f is two-dimensional. Then, of course, you can use the rank nullity theorem. And the rank nullity theorem says the dimension of the domain, in this case U, is the dimension of the image plus the dimension of the kernel. We know the dimension of the image is 2. We know the dimension of U is 2, so that means the dimension of the kernel must be 0. And of course, you are allowed to use that argument in the exam. I'd even encourage you to do that. It's a very clever argument. You should use that. And when you know the dimension of the kernel is 0, there's not a lot to compute, because the only 0-dimensional kernel is the one that consists of just the 0 vector. Please don't use the empty set here. It's not a vector space. Right? So the 0 vector is the right answer. The dimension is 0, and if I'm asking for a basis, just to complete that, basis of the kernel would then be the empty set. Right? So if you have this setup, no more computations are necessary. You know the kernel already. And I would not only encourage you, I would also expect you to come up with a clever way of doing that. So that answers this question, hopefully. If we have an affine linear subspace and we find out it cannot be a linear subspace, so in 2 dimensions, for example, we have a setting like this. Say this is the space that we're talking about. Let's call it U. Affine linear subspace. We found out it can't be a linear subspace, for example, because we can verify the origin is not included. So it can't be a linear subspace. And now we want to prove that it's an affine subspace. And what we usually do is we transform that, we translate that so that it contains the origin, and then we investigate whether this translated space is now a linear subspace. And the question is, how can we determine this translation vector? The answer is any vector in that space will do. If you look at that graphically, if you translate, for example, by this vector here, that point here, that's included, in that space. If we translate by the negative orange vector, we'll always get back to this translated space that now contains the origin. Same thing is true if we use this vector here, right, the negative green one. Same thing is true if we use this vector here. So actually any point will do. And of course you have to find a point in that space somehow. And the question of how to do this, I can't answer that. That depends on how that space is defined. That might be easy to see, or it might be very hard, depending on how the space is given. But you have to find a point in that space, and then you can just use that. Anything, any point will do, so just use the one that's easiest to get. All right? I hope that answers this question. And I think I have one or two more. One more. Please explain again how we know when we have to express a vector with respect to a different coordinate system. Very hard to give a general answer to that. So basically, in most cases, either the problem statement will say that, express that vector in B coordinates or something like that, and then of course you should do just that. Or the problem statement will not mention any coordinates. If it doesn't, just use canonical coordinates. Right? So if it doesn't mention any other coordinate system, it's always canonical coordinates. Of course, if you do any computations based on some matrix given in a specific coordinate system, then it's your responsibility to mention that this result is in B coordinates or something like that. But that depends on where you come from. So if for your computations you use a matrix that works in a specific coordinate system, then of course the results are always in that coordinate system. As long as you don't transform explicitly, you always stay in that system. I think that's the most I can say to that. If that was triggered by a specific situation, then feel free to approach me on Thursday or after this lecture, and maybe I can take a look at that and give a better answer. Let's see, there's also some questions I wanted to quickly answer in here. I did that already. I did that. Is it normal that this topic is extremely complicated for students? Nice question. Nice question. I'm not quite sure what you mean by this topic. I'd say, in my experience, basically the last 3 weeks are the most complicated of this whole semester. So basically it started with game theory. That is challenging for most students in my experience. Next week was matrix representations. That's not exactly easier. That's a pretty abstract topic, and I think it's pretty hard to grasp that. And then we're talking about scalar products and projections right now. That should be a little more familiar to some of you at least, but still this projection thing is a little harder to grasp. And I realize that is true. So questions about that, either they're more on the computational side. For example, I would expect all of you to be able to perform Gram-Schmidt. If I just give you the vectors and say compute an orthonormal base, that should be easy to do. But more complex questions, I'd say, are quite hard in most cases. And that doesn't mean they will not be on the exam. They will be on the exam. But I know that those are hard questions. So there won't be only hard questions on the exam, right? I'll try to make it fair. So it also contains some easy questions, some medium questions, and then some hard questions where you can actually shine, show your excellence. But if you just want to pass, then it might not be necessary to have all the answers to all the hard questions. Okay. I think there was at least one more question I wanted to answer. the evaluation is anonymous. So someone asking about that. Yes, it is. So I will only get aggregated results, and I don't know whether they store that somewhere, but I don't have access to any of your personal data there. I will not know who of you submitted which evaluation results. Right? So I will get all your comments, but I will not get any names attached to them. And for all the point marks that you're giving, I will only get the aggregated results. All right. And I think we can go on. Good. So next thing on my list is taking a look at some quiz questions. I have one that we will hopefully be able to complete today, and then we'll do more of those tomorrow. I picked one of the questions that most of you probably found hard. That's quiz question 14. Consider this basis B here and a linear function defined by the matrix with respect to B. And the question is to determine the representation of F with respect to the canonical basis. All right. You did all do that, hopefully. So we can skip right to possible approaches of how to solve this. And basically, for questions of this type, there is always at least two approaches. One is to use a transformation matrix. And one is to use this rule that the columns of the matrix contain the coordinate vectors of the images of the basis vectors. Sounds complicated, but we've used that. I'll talk about that in a minute. I'll just like to show you the easier approach, in this case, with the transformation matrices first. Right, so that's the first possible approach here, using transformation matrices. And the first question is, we need to find out which transformation matrix we need. Well, in this case, we have two bases. We have B and we have C, right? B and the canonical basis C. We want FC, and we have FB. So what do we need to transform and where? Well, here, on the right-hand side of this matrix, we need to have a vector in C coordinates, right? FC takes C coordinates and gives C coordinates. So the result that we'll get is also in C coordinates. Here, the input needs to be in B coordinates and the output is in B coordinates. That means if you want to be able to feed C coordinates into this matrix, we need to transform them to B first. So that means the first transformation we need here is the transformation from C to B. Right? And remember, the same system always meets here when we do matrix multiplication, so there's a B and there's a B here. And then afterwards we get a result in B and we need to transform that back to C. So again, B output here, B input in this transformation, and then we get C, and that's what we want. Right? So this chain on the right does the same thing as this matrix on the left. We have this here already, so all we need to do is determine those two. And now let's figure out which one of those is easier. Let's see. If we start with B coordinates and want to transform into C coordinates, right? What do we have to do? Well, remember, B consists of those three vectors. The B coordinates of those vectors are 1, 0, 0, 0, 1, 0, and 0, 0, 1. the first, the second, and the third coordinate vector after all. And those are then the C coordinates of those vectors. So it's very easy to get from B to C because the C coordinates are written in that basis already. Right? So that's what we want. So if you want to get from B to C, that means, well, the first B vector transforms into this vector here, 1, 0, 0. So that's the first column of our transformation. The second B vector transforms into this C vector, 1, 1, 0. And the third B vector transforms into this C vector, 1, 1, 1. So that's the transformation from B to C. And then we also need the other way around, the transformation from C to B. And that's the inverse of that first matrix. Right? So our next task is to invert. And we do that in the usual way. We write down that matrix, we write down the unit matrix, the identity on the right, and then we do Gaussian elimination to get an identity on the left and the inverse on the right. Right? And in this case, that is pretty easy to do. We just need to, let's see, subtract the third row from the second and the first one. We already have this lower triangular form here, right? So we can start with the upper triangle right away. And let's see, what do we get? Here we get 1, 1, 0. And on the right, we get 1, 0, 1, 0, minus 1. And for the second row, we get 0, 1, 0. And on the right, we get 0, 1, minus 1. And the third row is unchanged. And then we need to subtract the second row from the first ones to get rid of that plus 1 here. So that yields 1, 0, 0. So we have the identity on the left, and on the right we get, let's see, there's a 1, minus 1, and minus 1 plus 1 is 0, and all the rest is unchanged. Okay, so this is our inverse, 1, 0, 0, minus 1, 1, 0, 0, minus 1, 1. Very nice. Okay, and now we just need to do the computations. Remember, we want FC. FC was the transformation. Let me just write that down first. So written from read from the right to the left, because that's how we apply those matrices. We transform from C to B. We apply F in B bases, and then we transform back from B to C. Right, so that's what we want, and that means, let's see, the CB, that is this matrix here. Let me just copy that here. Come on. Then this FB that was given in the problem statement, I should have copied that. That is 1, 1, 2, 1, 1, 2. I think it was 2, 0, minus 2. Is that right? Yep, and 0, 0, 1. And then we have this transformation from C to B, which is this one here. So 1, 0, 0, minus 1, 1, 0, and 0, minus 1, 1. Right, and now we just need to compute that matrix product here. It doesn't matter which you start with, right? The order, of course, matters, but then which pair you do first does not matter. So let's just do the first pair first. That will give us a, let's see, a 1. No, actually not. That's 1 plus 1 is 2 plus 2, that's 4, right? Yeah. Then we get 1 plus 2, that's a 3, and a 2. For the second column, we get 0, minus 2, minus 2, and for the third column, we get 1, 1, 1. And then we multiply this with that inverse matrix here. And let's see, result is 4, 3, 2, minus 4 plus 0, minus 3 minus 2, that's minus 5, and minus 2 minus 2, that's minus 4 again. And then let's see, that is 1, 2 plus 1, that's 3, and 2 plus 1, that's 3 again, right? Right. So that hopefully is the correct result. I didn't actually check with the quiz results, to be honest. Any questions up to this point? So the order of these three factors does matter, of course. Yeah, you can't interchange those. But whether you first do this multiplication or this, that does not matter, right? So in other words, matrix multiplication is associative, but it doesn't commute. Any other questions? Yeah. Could you try to speak up a little, please? Yes. I just copied the base correctly. So again, my argument is this. This transformation, let me write that down once again. That transformation matrix here, that was this one, right? 1, 0, 0, 1, 1, 0, 1, 1, 1. And that was, I said, the transformation from B to C. Now what that does is it converts B coordinates into C coordinates, right? If we look at this vector here, let's take that last one first. This vector here, that is given in C coordinates. If I want the B coordinates of that vector, what do I have to do? I have to find a linear combination of the basis vectors in B. And then I take the coefficients of that. And obviously, I mean, it's the last vector, right? So obviously the right combination is take this vector once and all the others 0 times. So the B coordinates of that are 0, 0, 1. Well, that means if I multiply this matrix here by this 0, 0, 1, what I get is the last column. Yeah? That's exactly the third column of TCB. So the third column needs to contain the C coordinates of my vector, and the C coordinates are just this vector here. And the same argument works for the first and the second vector. Right? So that's why it's just the basis vectors. You just need to make sure that you get this order here right. Oops. This here, yeah? So don't mix that up. One of those matrices is always easy, you just write down the basis vectors. Just need to make sure which one. And then the other you get by inversion, and then it's just matrix multiplication. Yeah. So conceptually that should not be hard, but of course it's easy to make a mistake. So you should pay attention to carefully doing your computations here. Any more questions? Otherwise, let me maybe briefly mention this alternative approach that I've talked about. Let's see, maybe I can copy that over. Obviously not. Oh yeah, I can. Good. Or not. Here we go. Okay, so here's it again. I also said the other possible approach that I would not recommend in this case, but that might be better in other cases, is this rule that for this FC, well, what are the columns of FC? You remember the first column contains the C coordinates, because we want FC, right? C on both sides contains the C coordinates of the image of the first basis vector of C. The coordinates are always due to this output. So this here determines which coordinates I want in that matrix, and which vector I take as the input, first basis vector of C in this case, that is determined by this right coordinate system, right? If they are different. If they're the same, then of course it's both the same, but they might also be different, and that rule will still work. Same is true for the second column and the third column. That contains the C coordinates, that doesn't change, of the second and the third basis vector. Yeah, let me briefly write that down as well. So the second column contains, again, the C coordinates of the image of the second basis vector of C, and same thing for the third column, and so on. So that's also a way you can use to compute that. You just need to take these basis vectors here, put them through F, so compute their image, and then take this image and compute the correct coordinates for that image, and you put those coordinates into the columns. That might be easier depending on how F is defined. In this case, it is pretty complicated, and I'll show it just with maybe with the second basis vector. We just do that as an example. Example for the second column. And the others work similarly. I'm not using the first one because that's easier. All right, so that second column. Now remember, we want the second basis vector of C, right? Second basis vector of C, that is 0, 1, 0. We want to compute the image of that. So F of 0, 1, 0. How do we do that? Well, we only have F as its matrix representation with respect to B. So that's the complication here. We don't know how to compute an image of C vectors, only of B vectors. So first thing we need to do is find the B coordinates of that. So we need to find the B coordinate vector of that, and then we can put that into our matrix, because that works with B coordinates. That can't work with C coordinates. Well, how do we do that? Well, as we usually do. Here's the basis B. And now we want to find the right linear combination for that. Let's see, obviously we need to take this last vector here 0 times, because otherwise we would get something other than 0 here, and we don't want that. So there's 0 here. Then we need to take this here once, because otherwise we couldn't get this 1 back. So this is 1. And now let's see, we have in the first line we have 0 plus 1, and we want a 0, so we need to take this minus 1 times. And now we get minus 1 plus 1, that's 0. 0 plus 1 plus 0, that's 1. And in the last row, we have zeros. Okay, so our B coordinate vector is -1, 1, 0. We can now put that in our matrix FB to get the image. So FB times -1, 1, 0. Let's see, FB was 1, 1, 2, 1, 1, 2, 2, 0, -2, and 0, 0, 1. Times -1, 1, 0. And we'll get, let's see, -1 plus 2, that's a +1, -1 plus 0, that's a -1, and -2, -2, that's -4, hopefully. So this is the result of this FB, and remember, FB outputs B coordinates, right? So this here is in B coordinates. We want the C coordinates of that thing. Right? So that's the next that we need to do. We need to determine the C coordinates. How do we do that? Well, we know the base is B, right? This is 1, 0, 0, 1, 1, 0, 1, 1, 1. And those B coordinates are interpreted as coefficients for those vectors. So this is 1 times this, -1 times this, and -4 times this, and we just add that up. So what we get is, let's see, 1 minus 1 is 0, -4. Then 0, -1, -4, that's -5. And 0, 0, and -4. And now these are the C coordinates. So that finally is the second column of our matrix. Second column of FC. Okay, so we go from C to B, we compute the image in B, and then we go back from B to C. Doesn't get much more complex than that. And if you compare, hopefully that should be the same result as before. Let's scroll back and see, and where's our matrix? Here it is. I'd say that looks good. Right? So I hope you agree with me that this first method was far less work in this case. In this case, we only got one of those columns after all. We'd have to do the same thing for the first and the third column as well. But it might be worth knowing that, because if F was defined in a different way, that might actually be the faster approach. That's why I wanted to discuss both. All right, any questions about that? Yes. I think we did examples where that is faster in sheet 7 somewhere, didn't we? I can see if I find something. I don't have the numbers available right now, but take a look at sheet 7. There should be some that use this method and it's pretty fast. Yes. Sorry, is there? Is there a way to see that a second method might be? It all depends on the definition. If I have a matrix defining F, and usually it's the fastest way to use this matrix and just do transformations with that. Yeah, if F is defined differently, then often that second method will be better. But that's just a rule of thumb. Could also be wrong. Any other questions? That does not seem to be the case. There's 3 minutes left. Well, that doesn't take us very far. So I'd say we'll go on with more questions from the quiz tomorrow. And if need be, also on Thursday. I hope I can answer some of your questions on TweetBack on Thursday as well. So please, if you have any more questions, put them on TweetBack. I'll look through all of them. I'll select some for Thursday, and I'll answer all the rest online. I'll see you on Thursday then.